We're going to do a quick addendum here to prove a statement we made earlier. We showed that Tm T plus n is less than or equal to Tm Tn, where it's assumed to all be over the same set E. So I just don't want to write that every time. Which is sometimes referred to as being submultiplicative. So at least that's what I'm going to call it. Maybe it shouldn't be called that because there's a plus here and then multiply here, but that's what we're calling it. So we were trying to say that the Tn, which I guess doesn't have the absolute value, it's included there, Tn to the 1 over n converges to the infimum of that set of all the 1 over k's, 1 over whatever letter. That was used in some of the later proofs, so we want to verify this. And again, the idea was that the Tn's themselves may not converge, but their roots will. So let's see why this inequality here implies that. And it's just some fairly straightforward real analysis, but it was hard to come up with exactly how to make it work. But let's fix an M in Z. Or an N or Z plus, whichever notation you prefer, positive integers. So TKM is equal to TM time plus M plus ... plus M, which is less than or equal to Tm, these all multiply together, or Tm to the K power. Then apply the power of 1 over Km. It's a little caret sign there. So we get TKM to the 1 over Km is less or equal to Tm to the 1 over M. Now that's going to be true for every K. So we have then that, let me erase this other piece. We have the subsequence of multiples of K is bounded above by the first one, Tm to the 1 over M. Okay, I wanted to say it was decreasing, but I don't think that really shows it's decreasing. It just shows that the first one, Tm, is greater than or equal to. Did I do something wrong? Let me make sure I didn't say this. No, that's right. Yes, okay. The K over M counts out the K and left with an over M there. So the Tm to the 1 over M is greater than or equal to any of the ones that come later, any of the later multiples there. So with this said, we'll now say we'll take an arbitrary n, and so we'll look at by the division algorithm, this is a classic piece of number theory, n equals km plus r, where k and m are both positive or greater than or equal to 0. M is not 0, but k is greater than or equal to 0, and r is less than, strictly less than m. So it's division with a remainder. You divide it into k groups of m with a remainder r. So we could say that Tn is equal to Tkm plus r, which will be less than or equal to Tm to the k, and then Tr. And then we'll apply the 1 over n power to both sides. So we get Tn to the 1 over n is less than or equal to Tm to the k over n, Tr to the 1 over n. And then we're going to do a lim sup of n here. And I don't want to use limit because that would be, we haven't proven this limit exists. That's what we're trying to prove here. So that would be a begging the question there to use the limit before we've proven that it exists. But lim sup always exists, so we don't need to worry about it there. At least always exists for bounded functions, and I do believe we've proven this is bounded above already. Maybe not, but it's there. Like we proved each subsequence is bounded above by m. So let's see. Okay. Now, just by the way we constructed n and k, n is mk plus r. So as n goes to infinity, k goes to infinity as well. So if we can look at this as divide by k here, n over k equals m plus r over k. So we can say n goes to infinity implies k goes to infinity as well. But r does not go to infinity. R is fixed, so that part is going to zero out. And so therefore, the limit n over k as n goes to infinity equals m. With that said, then we can reverse that and say the limit n to infinity of k over n equals 1 over m. Because m is not 0. The way we constructed m was positive. So then going back up here, this gives us lim sup n to infinity of Tn 1 over n is less than or equal to lim sup as n to infinity of Tm to the k over n, and the lim sup n to infinity of Tr to the 1 over n. Now 1 over n is going to 0, so that power goes to 1, so it's gone. So we have this expression here. But since we said Kn goes to 1 over m, so this equals T m to the 1 over m. So what we just showed, the lim sup here is less than or equal to Tm 1 over m for an arbitrary m, or another way of saying this might be the lim sup is less than or equal to the infimum of Tm to the 1 over m, where m is in z plus. Why is that good? Well, that's pretty much everything. And if you're good at real analysis, that's obvious. If you're not that familiar, I'll just briefly say the idea here being lim sup is the supremum, the least upper bound of the subsequential limits. So any subsequence will have to converge to something less than or equal to the smallest element of this entire set. Well, yeah, so if all the sequences, none of them can converge anything below it, below the smallest thing, the infimum, they must all converge to it. So therefore, the limit supremum, the greatest subsequence being less than the lowest thing, must mean that the limit itself is that. So limit is n to infinity of t sub n to the 1 over n equals the infimum across all m and z plus of t n to the 1 over n m. Therefore, this limit exists and it equals the infimum. And so we will define this as the Chebyshev constant for E. And there we go. All right, that's that. Thank you.